Do-do-do. All right, see my screen?
Yeah, I can see it.
Okay. And I should denote this as 3 frames. Okay. So clock policy. All right. So very similar to the other ones. At least for the first steps, you're going to be inserting these page frames in, just like how you've been doing for first come first serve and least recently used. But clock policy is going to introduce two additional rules as you kind of insert these numbers in. So first of all, we're going to introduce something called a pointer. So the pointer is going to decide where you're going to replace the page or place it rather if it's empty. Okay. So for the first couple numbers, it's pretty simple, right? Just like first. God, I always confuse this. First in, first out, right? So we will first have to insert number 2. And the second thing that the clock policy is going to introduce is that we'll have a little bit of like a use bit right here. And I'll explain what this means in just a second. Okay. But it's the same thing you've been doing. You're going to insert the, actually, let me do it this way. So first we insert the 2 use bit, right? And what you're going to do is you're going to move this pointer down 1 because the very, or the, when it's empty, right? The pointer is going to point to the blank page and it's going to move it to the next one. So the pointer is going to go down because this has been filled. Does that kind of make sense so far? So like in a nutshell, I know I kind of ramble a lot, but you fill the number in and then you move the pointer down. Let me actually pop the chat on in my phone real quick so that I can see this side by side. Okay. So, wait, you guys can see my screen, right?
Yeah,
Okay,
we
perfect.
can see it. We can see it.
Cool, cool. So, okay, so next number, so we'll have, 2 with a use bit, and then we're gonna insert 3 because that's where the pointer is pointing to, right? So 3 with a use bit, and then the pointer is gonna go down 1 again. Okay. So the next one, like other algorithms, right? If a number already exists in defaults, you don't need to do anything. There's nothing that needs to be done. So 2 use bit, and then 3 use bit, and the pointer does not move because nothing's changed. So once again, because 2 already exist, do nothing. Okay. Now place 1 in. So 2 use bits, 3 use bits, and then we're gonna put 1 in, and round robin style. We're going to move the pointer all the way back up. So the pointer is going to go here now because we only have 3 frames. Any questions on this part? That was the easy part. Okay, cool. All right, so back up, and now we have to insert 5. Now this is where it gets really tricky. Okay, so yes, it matters a lot, and I'll explain what that like does right now. So because this is so, I'm going to denote this as specifically use bit, so it's perfectly clear. Okay. Now, what a use bit means is that if a page has a use bit, that means it's being used. Okay, so that means we can't replace it. Okay, so not replaceable. So what that means is that if I want to replace 5, because that's where the pointer is pointing to, we need to replace this 2 right now. I can't do it. So what do we have to do? I'm going to write this on the side. So 2 with a use bit, and then 3 with a use bit. This is the current state right now. Okay, so 1 with a use bit. I'm sorry for the terrible handwriting. I'm using a mouse. So what we need to do is we need to remove the use bits and then move the pointer down 1. So we need to basically clear this page fault in order for this 5 to fit in. And what that means is, so the next step is going to be 2, and then we erase the use bit, and then we point it down 1. So 3 with a use bit, and then 1 with a use bit. So once again, because 2 has a use bit, we can't replace it because it's being used. What we do is we mark it off and then move the pointer down 1. And now we ask ourselves, is 3 can 3 be replaced? And the answer is no, because it has a use bit. So we need to repetitively do this, right? We need to get rid of this use bit. So 3 is going to get cleared. And then we move the pointer down 1 again. So 1 with a use bit. Okay. And then now we ask the question one more time and we say, can 1 be replaced? And it cannot be because it has a use bit. So we just get rid of it and then we move the pointer all the way up because of round robin stuff. Oh my gosh. Okay. 2, 3, 1. Now we ask ourselves, can 2 be replaced? And the answer is yes, because it doesn't have a use bit, right? So it can be replaced, which means we replace it with 5 with a use bit. And then we move the pointer down 1, which is 3, and then 1. This is not round robin. No, I'm using the term round robin because it just basically moves the pointer back up. It's like a loop. Does that make sense? So because there's no more numbers to go to, after 1, it just goes all the way back up. So this is clock. Okay, only clock has this like feature of use bit of the pointer. So because we replaced 5 successfully now, we just write it down in the pages. So 5 use bit, 3 don't have a use bit, and then 1. Okay, without a use bit. Why do you have 2 columns of 2 and 3? 2 columns of 2 and 3. Well, because so at this step right now, right? If we want to replace 2, well, because 2 already exists, right? I don't need to do anything because 2 already exists. Simple as that. So just do absolutely nothing if a number already exists. So very good question. Somebody asked what we need to write that whole sequence or straight to that. So you don't need to show your work here technically. Now, what you do need to show on your exam is you're gonna be formatted like this. Okay, you need to write down the pages. So like you need to write down 2, 2, 3, and then right next to that box, you're going to have like a use bit like box. So you have to check it off. Like if there is a use bit, you write 1, and if there's not a use bit, you write 0. So you'll have to do it for every single page. So for instance, like in this format right now, it'll be 2, 1, right? 2, 1, 3, 1, etc., etc., etc. So you just have to basically denote if it has a use bit or it does not. Does that make sense to everyone? But basically, again, just track the use bit, right? If it does have a use bit, you can't replace it. You have to get rid of it and move the pointer down 1 until you find a number that does not have a use bit. That's basically this whole entire algorithm. If you can understand that part, it's not that bad. So moving forward, can't watch the stream for some reason. Can someone else record or live stream my end? Yes, thank you. Whoever did that, thank you so much. Okay, I'll just give it like 3 seconds. Okay, cool. So moving forward, now we're at the spot right now, right? So we just finished 5. I had this quick read. So now we need to replace 2, and because the pointer is pointing to 3 right now, and does it have a use bit? It does not, right? So can we replace it? And the answer is yes, right? So 5 use bits, and then you replace the 3 because it does not have a use bit. Very important, okay? Because 3 doesn't have a use bit, then you can replace it. So therefore, you will have 2 with a use bit, and then move the pointer down 1, and then just keep the 1. That is the ugliest 1 I've ever drawn in my entire life. 1. There you go. Does this make sense to everybody so far? Because this is basically it. Like that's the entire clock policy right there, pretty much. Okay, question. If there's a repeat number and the duplicate number in the sequence does not have a use bit, we'll get to that. That's a very good question. So, and the answer to that is that you will have to mark it as a use bit, but we'll get to that. So there will be an example coming up. But very, very good question. So now we have to replace 4. So same deal, right? 5 use bits, 2 use bit, and then because 1 does not have a use bit, we replace 4 with 1 with a use bit, right? You move the pointer all the way back up. So the pointer is now right there. God, this is like terrifying to look at. Okay. All right. So 5, and because 5 already exists, right? What do we need to do? We do absolutely nothing. So just keep the pointer, just repeat. So 5 use bit, 2 use bit, and then 4 use bit. Okay. And then I'm gonna just like move that like there a little bit. Okay. And then I honestly didn't know that you can even do that. But anyways, so now we need to replace 3. Same, like exactly the same deal, right? So I'm just gonna write this down one more time. So 5 use bit, 2 use bit, yada yada yada, 4 use bit, right? So now we need to replace 3. And what we do is we get rid of the use bit because that's what the pointer is pointing to, right? So 5, get rid of the use bit, and then move the pointer down. So 2 use bits and 4 use bit. Same deal. So get rid of the 2 use bit, right? And then you move the pointer down 1. So 4. Okay, this is getting just uglier and uglier to look at. So 2, 4 use bit. Okay. And then we clear the 4 use bits, right? And then you just point it all the way back up. And then once it's pointed all the way back up, we need to replace it. So this will be, I need to sneeze, sorry. All right, bless me. So 3 use bits, and then you move the pointer. I hate that 3, I'm sorry. 3 use bits, and then you point the pointer down 1, 2, 4, just like that. Thank you, thank you, thank you, thank you, thank you. Okay, does that make sense to everybody? Okay, cool. Now, so to repeat the question somebody else asked, if there is a repeat number and the duplicate number in the sequence does not have a use bit, do we still ignore it? Now, in this case, right, 2 already exists in the pages, but it doesn't have a use bit on it. And we're using 2, right? Because we need to use 2 now. So what do we need to do? We need to actually mark it as a use bit. I'm going to denote this as a red color just so that it's perfectly clear. So 2, and now you need to turn this use bit on. Okay, make sure this is actually turned on. So there's a difference here. My gosh. Pointer and then 4. Okay. And once again, because the previous 2 does not have a use bit, okay, and we're using 2 now, that means we need to turn the use bit on. Does that make sense to everybody? Hopefully. And then a very good question somebody might ask is like, what do we need to do with the pointer? Do nothing. It doesn't even matter where the pointer is. Yes, the pointer will not move. Even if it's on 3, you still keep it there. Okay, that's the very common mistake some people make. So the whole point of, turning on a use is that it's like saying, I have a process that's not running right now, and now I need it to run. You obviously have to turn the use bit on, but the pointer doesn't change. It doesn't really decide to go to another location because it's not being replaced. It's simply like toggling a switch on. So that's the best analogy I make. So the pointer stays in this case because you're just turning a use bit on. Okay, so moving forward, we're just gonna go a little bit quicker now. So 3 use bit. Oh shoot, actually, I'll just do it. So 3 use bits, and then because there is a use bit on 2, we need to clear it, right? We need to clear it. So 2 is gonna get cleared, and the pointer goes down 1. And then because the pointer is pointing to 4, and 4 does not have a use bit, and it gets replaced by 5, right? So this gets replaced by 5, and the pointer will go all the way back up. What do you have had? What if you had 3 pointer, 2, 4, and see a 2? Yeah. So by Sue. So somebody just asked if there is like. Okay, I'll just write this down real quick. I'll just write this in like green. So let's just say like if there's a 3 pointer, or excuse me, 3 use bits, 2, and then a 4. Okay, and we see a 2, right? So we need to replace 2. Now, because 2 already exists, all you're doing is just turn it on. That's it. You just turn this thing on. That's it. That's all you're doing. You turn it on and you don't move the pointer at all. Keep the pointer there. It's like all you're doing is just toggling a process on. That's all you're doing. Quote unquote. You're not really toggling a process, but you're just replacing pages. But yeah. Okay. Hopefully that makes sense. Okay, so going back, And then now we need to replace 2. And okay, this is literally like I just repeated whatever I just said, right? So 2 already exists, but it doesn't have a use bit. So what do? We just turn it on. That's it. We don't do anything. Oh my gosh. So we just pointer, or excuse me, pointer and a use bit. So 2 with a use bit on, and then 5 with a use. I guess I kind of want to just denote that as red, just because I just so that everybody recognizes that there is a little bit of a trick here. And then 5 with a use bit, and voila, there you go. That's it. Wait, why was the 2 turned off in the second last column? Right. So okay, I'll write this in another area. Okay, so we're at this part right here. Okay, and this part right there. So we're at 3. Oh my gosh. So 3 use bits, and then what is it? 2 use bits, and then we have a pointer pointing here, and then 4. Okay, and we need to replace 5. 5 is what we're replacing, right? Because that's the next number that we have to replace. In this case, right, because 2 already has a use bit on, when 2 has an already used bit on, what do we do? Because that's where it's pointing at, right? Okay, sorry, I'm just trying to read the chat real quick. Okay, yeah, Sue asked the question. Sorry. So Sue, right? When there's a use bit on right here and that we're pointing to it, what do we need to do? We need to turn it off, right? So turn this thing off, and then 3 use bits to turn it off, and then the pointer goes to the next one, right? And then when the pointer goes to the next one, it's pointing to 4. It doesn't have a use bit, so we just replace it, right, with 5 with a use bit, and then put the pointer back up, and that's exactly how we got here. I don't know if you can see my cursor, but where 5 is landing on right now. So again, like in a nutshell, I'll just put a text here. So maybe not this big. So clock policy. Pointer points to a use bit, remove the use bit, and move the pointer down one. Okay? If no use bit, replace that number. And then the special condition is that if a number already exists and does not have a use bit, turn it on, keep pointer. So that is literally clock policy in a nutshell. Any questions on that regard? Okay, if there's no questions, I don't really know where we're going next, actually.
I'm gonna do the unit processor scheduling algos.
Cool. I will turn this off then, and I'll hand to Cameron to do the rest. Okay, cool.
Okay, friends. If you need to lock in, now is the time. This is about 25% of your exam, okay? And again, you're not going to have the Excel, which, I'm not going to lie to you, the Excel was useful. I never ended up using it, but about 99.9% of other people ended up doing it. So you're not going to be able to use the Excel, which is going to make this pretty difficult, but that's why, again, I'm doing this on hand to show you guys how to process this, okay? So first, you're going to get something like this. It's going to tell you that there's a unit processor scheduling algorithms. Each are going to be worth 5 points or so, and they're going to give you different ones, okay? And so the first one is most likely going to be something called first come, first serve, okay? And they'll label it like this, so you'll know what you're working with here. And if you haven't researched or whatever, and you don't know what a uniprocessor scheduling algorithm is. I'll show you, but essentially it looks something like this. So you're going to have some processes. You have A, B, C, and D. Okay. They're going to have something called TA, and they're going to have something called TF. Okay. Or I'm sorry, TS. The TA stands for time arrival. Okay. So TA stands for arrival. Okay. Now this means when is this process arriving? And they're going to give you numbers. So I'll just say 0, 2, 4, and 6. Okay. And then there's going to be something called service time. And this is the amount of time it's going to take for the process to actually do its job. And sorry, this S is bugging me. Okay. In this case, we'll just say 3, 5, 4, and 1. Okay. Now it's your job to figure out the finishing time. So at what point do these processes finish? So it'll look like this. Okay. It'll be TF or T finish. And you need to also calculate the turnaround time, aka the TR. The TR is equal to TF minus TA. This is a hard formula. Please write it down. Keep it in mind. You're going to use this for every scheduling algorithm question, and this will make more sense in a second. Okay. So let's first understand what a uniprocessing schedule is, so that we have a basis for the rest of the examples here. First off, there's something that I really need you guys to do for me. I need you to write down a queue. Okay. Now, this is just going to be so important. I cannot stress how important this thing is going to be when you're doing these, because you're going to get lost. If you don't have this queue and you're not keeping track of what you're working with, it's going to be kind of difficult. Okay. Now, to start off here, we're going to have like a linear time thing here. Okay. So we're going to have a line, and it's going to look like this. It's going to look like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12. Okay. You can go ahead and draw this every single time we get to this question. Okay. Every single time. And you could add a little markers here if you'd like. Okay. But you're going to draw this. And at this point, I'm not even recommending. I'm telling you what you're going to do. Okay. Because if you don't do this, good luck figuring it out. Okay. And now on the left side here, it's going to look kind of like a graph. You're going to have your processes. Okay. You're going to have these processes. Okay. So you're going to have A, B, C, and D. Okay. Now, this is what we're going to be working with. Okay. And first come, first serve is super simple. And it's a great introduction to what exactly we're going to be doing. We have TA. What does TA mean? TA means time arrival. So this is going to mean, when does the process arrive? A is going to arrive at 0, B is going to arrive at 2, C is going to arrive at 4, and D is going to arrive at 6. Those are where it's scheduled to arrive. Once it arrives there, how long is it going to take to actually process? Well, A is going to take 3 times, like 3 time notches or whatever. B is going to take 5, C is going to take 4, and D is going to take 1. Okay. So all we have to do in first come, first serve is we start in lexicographical order, meaning we're going to start with A, and then we're going to go to B, and then we're going to go to C, and then we're going to go to D. Okay. So when we start with A, we see that it arrives at 0. So it's going to arrive like right here, and it's going to go for 3 times. So it's going to go 1, 2, 3. Okay. And let me draw this a little better here. But you see A is going to go for 1, 2, and 3. Okay. And we're done with A. That's it. That's all you got to do. Okay. So our queue here, we start with A, then we start with B, and then we go to C. This is what our queue looks like. Now, if we look up here, we see, oh, okay, B is supposed to arrive at 2. So B is supposed to arrive right here, but A takes 3 times. So what do we do? Well, it's first come, first serve. So because A started first, we're going to let A play out, okay? And then we're going to start B once A is done. So now you'll see here, our queue, we're done with A, and now what's next? We're going to move on to B. And because it's first come, first serve, we're just going to go in this order. That's all you got to do for first come, first serve. So we see here B arrives at 2, but, well, we've already taken up 3 with A, so we're just going to go ahead and start at 4, okay? So how long does it take? It takes 5 notches. So 4, so 1, 2, 3, 4, 5. Okay. And actually, I did that a little low. I meant to do that up on B here. Okay. So everybody follow along so far. Does everybody get this? Because you gotta get this very simple one before we start getting into the complex ones. Okay, so that's B. Everybody get it so far? Why are we starting at 4? We start at 4 because A has already taken up the first 3. Okay. What do you mean corner to corner? I mean, it is corner to corner, but
Cameron, I think it's 0 base. So you do actually have to start from 0 to.
Oh, do we start at 0 to 1? Is it 0 base?
Wait, yeah, it is 0 base technically because you're supposed to mark 1 as the. Yeah, it's supposed to go from 0 to.
It is 0 base.
Yeah.
I'm so sorry. Okay.
Yeah.
All right. So we'll just start at 0. Okay. So this arrives here. So we go 1 and then 2.
Yeah.
Like that. Sorry.
No, it literally goes from 0 to 3 because it has
3. Yeah. Sorry, I was reading it as 2. Yeah, 3.
Yeah.
You start from 0. So we go 1, 2, 3. 3 little slots here. I'll do it like this. This will be a little easier corner to corner, like you said. Okay. So sorry about that. I'm so sorry. So you see it arrives at 0. We start at 0 here. We're gonna go for 1 notch, then we're gonna go for a second notch, and then we're gonna go for 3 notches. Why 3 notches? Because that's its service time. Okay. Now again, B was supposed to arrive at 2, but that slot has been filled up because of first come, first serve. So we're just gonna go ahead and now fill up B for 5 notches. So here's the first notch, second notch, third notch, fourth notch, fifth notch. Okay. Okay. Does that look good, Jason?
Yeah.
That's correct. I'm pretty sure it is. Okay.
Yeah,
Perfect.
it is. Yeah.
All right. Does everybody understand how we got this? Yeah. It would be 0 to 3. I'm sorry. Yeah. You guys are right. My bad. Okay. So now we're done with B in our queue. Now we move on to C. Okay. So now for C, it's supposed to arrive at 4, but 4 has been taken up by B. So we're going to go ahead and now just start it wherever B left off, and it's going to go in for 4. So we're going to go for the first notch, second notch, third notch, fourth notch. What the heck? That was weird. Okay. So now C is going to be done right there. And I didn't have enough room. I'm sorry about that. But you would put, ideally, you'll have a big thing of paper, and you could put 13. So we'll just put like a little extra line here. Just say it's like 13. Now, C is over, and now it's time for D. So D is going to go from 12 to 13. Okay. Just label this as D. This is C. This is B. And this is A. Okay. All right. Does this make sense? Okay. So because D was supposed to arrive at 6, obviously that's been long gone. And if we follow our queue here, we see that D is last. And we just have to, it's first come, first serve. So we just kind of leave it wherever it was left off by the previous process. And it only takes 1 service time. So it's only going to go from 12 to 13. Okay. Fair share. Yeah, we're going to go over fair share. Wouldn't the sum of TA and TS be 13 as well? Yeah, the sum of all these would be, well, yeah, I guess you could look at it like that, sure. Okay. All right. So anyway, I'm going to speed this up now that we all kind of understand the concepts, right? The basic idea. Now, TF is just wherever the process finished. So if we look at A finished at 3. B is going to finish at 8. C is going to finish at 12. And D is going to finish at 13. Okay? Now, the turnaround time, like we said earlier, is just TF minus TA. Okay? So TF minus TA. So our turnaround time was 3. For B, our TF minus TA is 6. 12, so it'd be 6. And then 13 minus 6 it would be 7. Okay. So this would be our TF because this would finish, and then TR is just TF minus TA. Okay, is that good? Everybody good with that? Hope so. Let's move on here. Next up, you're gonna have something called round robin. Okay, it's gonna be the same process as usual, except he's gonna give you something called a quantum number. Okay, for this example, I'm gonna set our quantum number to 3. C is 8, right? Yeah, finishes at 8. Yeah. Oh wait. Oh, I'm sorry. I'm an idiot. Sorry about that. Yeah, I don't know why I put 6. It's 8. Yeah. 8. Sorry. Yeah, it's 12 minus 4. I don't know why I put 6. Okay. No, you're right. You guys are right. Okay, so now we're gonna go about round robin. Okay, it's gonna be the same thing. They're gonna give you TS. They're gonna give you TAs. So our TA and our TS for A, B, C, and D. We have 0. I'm gonna put 1, 1 and 4, 2 and 2, and 3 and 2. Okay. Now, of course, you're gonna have to come up with TFs, and you're gonna have to come up with the TRs. That's gonna be your final answer. But of course, let's go ahead and follow our cue here. Now, you can always assume it's going to be lexicographical order for now. So we'll go ahead and do A, B, C, and D. Okay. And let's go ahead and start drawing our thing here. Okay. So for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I know this is going to be a lot, and it's going to suck to do this on the test, and it's going to take a lot of time, but you know, that's just how it's going to be. So if we follow our cue here, we're going to do this just like how we did first come, first serve. Okay. And we're just going to follow this normally. All right. So let's go ahead and start here. We have, and again, keep in mind, we're doing RR or round robin. Okay. For here, we have A starts at 0 and it goes to 1. So very simple. 0 to 1, we can cross A off. That process is finished, so we're done. Okay. Now we have 1 to 4. The issue is that we start at 1, that fits, but our service time is 4. Now, according to round robin, your service time can only be as long as the quantitative time given to it, allocated to it. Okay. So 4 is greater than 3. So what's going to happen is B is only going to run for 3 notches, and then it's going to move to the back of our queue. Okay. So if it starts at 1 and we have TS of 4, we're going to go 1 notch, 2 notches, 3 notches. We're only doing 3 because of this queue right here. If this queue said 2, then we would only do 2 notches, right? Because this is still above 2, right? So any number, any TS that's greater than Q, you only do that, you only do the, like, whatever number is Q is saying, essentially. And then you keep the remainder. So now we have our B here. We've only done it 3 times, and it requires 4. So B is not done. So what we do is we take B and we move it to the end of our queue, and we say it has 1 notch left. Okay? Does that make sense? Because we already got 3 notches in, but it has 1 left, but this is restricting us. Okay, this is not allowing us to finish our process yet. Okay, does that make sense? So let's keep going now. We see that for C, the service time is 2. 2 is less than 3. So that, that falls into our thing. Okay, so we're going to go 1 notch, 2 notches. So C is done. Now we have D in our queue. Okay, so now we can say it's supposed to arrive at 3, but of course that didn't happen, so that's okay. Our service time is 2 for D. Okay, so we're going to go 1 notch, 2 notches, and D is done. What's left? B has 1 notch left. So now we're going to go back to B down here, and we're going to finish off its last notch. Okay? So does that make sense? What if no other processes C and D have arrived by the time B has reached the quantitative limit? That's fine. All that matters is that you just follow your queue, like I said here. With round robin, you're only going to adjust your queue whenever the quantitative time has been reached, the max time. Okay? So we do A, B, C, D just normally. We can do A because it's not in our quantitative time. We see B is excessive, so we take the difference and we allocate it to the bottom of our queue with the difference. And then we continue with C and D like normal. Okay? So now if we take a look here, our finishing time for A is going to be 1. Our finishing time for B is not going to be 4. It's going to be 9. Right? B finished at 9. For C, our finishing time is going to be 6. And for D, our finishing time is going to be 8. Of course, what is our turnaround time? Our turnaround time is our finish minus our arrival. So our turnaround is going to be 1, then 8, then 4. Excuse me. And then 5. Okay. So that is how you solve round robin. Any questions? Any questions about the quantitative time and our queue and the little remainder thing? Okay. Why did we add B minus 1 to the queue? We added B minus 1 because if you look here, its service time is 4, but our quantitative time only allows us to do 3 at a time. So we do 4 minus 3, and we allocate the 3 here, and we have 1 left. So because we did our 3, we have to move B to the back of the queue to only have 1 left. And then we can continue with C and D. So it's because of this queue up here is why we did that. Okay. This isn't B minus 1. This is just saying that B has 1 block left. Okay. Because if this were to be like 2, then I would have put a 2 here because it would have had 2 blocks left. Right. So that's why we did that. Okay. Let's move on. I don't want to take too much of y'all's time. Okay. Let's talk about SPN. Shortest processing time. Okay. Now, this one is pretty simple, but this one does involve really understanding arrival time and service time. Okay, so let's go ahead and say our T arrival and our T service with our A, B, C, and D. We're going to go ahead and say 0, 3, 2, 5, 4, 4, and 6 and 1. Of course, make sure you draw your queue. This one's going to be especially important in this. And we can go ahead and we can go ahead and just do our A, B, and C and D right now, but that's going to change in a minute. Okay. Of course, we need our TFs eventually, and we need our TRs. That'll be what you're solving for. And we can draw our long, that was my bad, that was not very good. We can draw our long graph here. We could say A, B, C, and D. Let me erase that. Sorry. Okay. Now we can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, And we're going to have to number this out. Again, please make sure you do this on the test. Otherwise, I really don't know how else you're going to solve this. Okay, and of course we have our 0 here. All right, let's take a look here. So we have 0 to 3. Now, during the shortest processing time next, you want to make sure that you are keeping track of how many notches are left. Okay, so if we start here and we know we can go to 3, what I would recommend is looking at the next one. So we see here that TA is supposed to arrive at 2 for B. Okay, so B is supposed to arrive at notch 2, but we see here A is supposed to take 3 slots. Okay. Now, this is pretty much the same thing. Essentially, what we're going to do is we're going to follow this. Okay. And we'll see here, let's do this. Let's do 2. And you'll see here that, well, B is supposed to arrive at 2, right? So, but A wants to take 3 times. So what's going to happen is, what is going to be prioritized? What's going to be prioritized is whoever has the shortest processing time. Okay. Now, processing time is the same thing as saying TS. Okay. This is equal to processing time. Okay. It's the same thing. So what has the shorter processing time between these two? Is it B or is it A? It's going to be A. A has a processing time of 3. B has a processing time of 5. So A will be allowed to finish its process. Okay? So A will be allowed to finish and go to 3. Does that make sense? Are we going to have a section for the queue to keep track of? No, you're going to have to write this down on your own. You're going to have to write all this down on your own. You're going to get nothing except this up here. This is all you're going to get. You're going to have to draw all this. Wouldn't it be 1 because we went for 2? Yes, this is correct right here. Yeah, if TS, wouldn't it be 1 because it went for 2? I don't know what I don't understand. But yeah, so let's say this processing time was 1, then this would be, and A would be interrupted and be moved to the back of the queue, and we would just interrupt it and do B. Okay. But we didn't do that because A has a shorter processing time. Okay. So now we can keep going here. And we're going to go ahead. Let's just do this. We see that this is supposed to arrive at 4. So, okay, something's going to happen at 4. So let's go ahead and do B. We're going to go and do B. We're going to do 1 notch. Uh-oh. C is supposed to arrive at 4, but B says it needs to go for 5 times. Which one has the shortest processing time? Is it C or is it B? The answer is C. So what's going to happen? B is going to be moved to the back of our queue. With how many remaining notches? We only got 1 off before we were kicked off. And its service time takes 5. So it's going to have 4 remaining notches left. And C is going to be now prioritized. Why? Because it has the shortest processing time. Okay, it has a shorter service time. Okay. Now, we see here that D is supposed to arrive at 6, so C is allowed to execute a few times. It can go once, then it could go twice. And uh-oh, D is supposed to arrive at 6. Okay, now we're at a competition. Who has the shortest service time? Is it D or is it C? The answer is D. So, now what happens? We move C to the back of our queue with how many left? We've already got 2 off on C, and there's 4 total, so it's going to have 2 left. Okay, and now D is going to be allowed to execute. So D is going to execute, and we can go ahead and finish off D. That's going to have its 1 done. Okay, now let's go back and look at our queue. After all this is done, and this is why the queue is so important. After we've done all these processes, what's next? Well, we have B here, and then we have C. So we're going to continue B for 4. So we're going to go back here. We're going to do B for 4 more times. So we're going to do 1, 2, 3, 4 for B. Okay. All right, that's all good. And now we can finally finish C. So we do 1 and 2. We do C for 2 notches. So this is what your final thing will look like once your Q is finished up. Why are we continuing B instead of C? Because earlier, do you remember what I talked about pushing it to the back of the Q? When we had an issue between B and C, B was longer, so we pushed it to the back of the Q, right? And then you continue with C because C was right here. We were at this step. And then we had a conflict between C and D. So we're finished with C, we start D, and we had to push C to the back of the Q. So then as we follow our Q, we did A, then we did B, then C, then D, then back to B, and then back to C. Okay. This is exactly why I was emphasizing the Q, right? Because otherwise this is going to get really confusing. Okay. So does everybody kind of understand? What if both have the same processing time? Great question. If both have the same processing time and it comes down to a conflict, you stick with whatever is going currently. Okay, so if B and C had the same processing time, we would just stick with B. We'd let B finish. It's in lexicographical order. Yeah. Okay. So you only check the shortest process when something arrives, and after just follow the queue order. Yeah, that's exactly right. That's exactly right. So you noticed I didn't care about any more the arrival time or whatever, because once we've executed all the main A, B, C, and D, then we're just following the queue. When it gets pushed back to the queue, do you compare against the other? Nope, you don't compare anything. Once it's pushed back, that's it. That's what it's going to do. Next time you reach it, you don't have to worry about anything else. Okay. Would it be possible for a process to end before the next process is supposed to start? Example, A ends at 3 and B, of course. Yeah. Yeah, I mean, that's ideal. You know, that's what you would like to have. Then you don't have to worry about this queue stuff. But yeah, that's completely possible. And then once you have all the service time done, you can just cross it off your queue. Okay. Give the CPU some breathing room. Yeah. Uh-huh. So, all right, so let's take a look at our final answer here. For TF, it's going to finish at 3. For B, our TF is going to finish at, looks like 11. Okay. For C, it looks like it's going to finish here at 13. And then for D, it looks like it's going to finish at 7. And of course, you can do the math. It's just TF minus TA, then TF minus TA, TF minus TA, TF minus TA, and that's how you're going to get your R's. Okay. All right. Everybody got it? Yep. I know it's a lot. I know. Trust me. Trust me. I know. Okay. All right. Last one for me, and then I'm going to give the last one to Jason. Let's go ahead and look at SRT, shortest remaining time. This one is pretty much the same. It's really not that bad. Let me pull up my example here. I'm sorry. Give me 1 second here. Okay. So for the shortest remaining time, we're going to have to keep track of what is left each time we do the process. So let's go ahead and do our A and B, C and D. We have our TA, which again, they'll give you, and our TS, which will give you. We have 0 and 4. Then we have 1 and 2. Then 5 and 3. Of course, 6 and 1. Then you need to find your time that it finishes at and its turnaround time. Our Q is going to be very important here. Okay. And of course, we're just going to assume always A, B, C, and D at the start before we start moving things around. Okay, sorry about that. Okay, yeah, sorry. All right. Now let's go ahead and do this. So let's go ahead and draw our thing. You guys are going to draw this. I better be walking around tomorrow and seeing this all over y'all's paper. If not, I'm going to take your paper because you will not be worthy of having it. 8, 9, 10, 11, 12. We'll just do 12 for now. If we got to do more, we could do more. But I don't think this goes on further than 12. Actually, it might. I don't know. Okay. Let's start here. Okay, so shortest remaining time is all about prioritizing what has the shortest time left as it's being executed. Okay, so you're gonna have to do a little bit of math in your head to keep track of what is left of our process. So let's start with A. Okay, so A is gonna start at 0. And it's going to start at 0 and it wants us to go 4 times. The issue is that B needs to arrive at 1 and it's only going to go 2 times. So what's going to happen? Well, we're going to go ahead and we're going to start moving. So we'll move it once and then here's our B wants to start. We've already done 1 notch. Okay. So how much time is left of A? 3, right? We've done 1 notch. It requires 4, so A has 3 left. How much time does B have? B has 2 left. So we're going to take our A. We're going to move it to the back of our queue with 3 left. And now B is going to take priority. Okay. So now let's go ahead and take a look here. We see that C arrives at 5 and B only takes 4, so or 2, so we don't really have to worry about this. So we can go 1, we can go 2. All right, voila, B is done. We don't have to worry about B ever again. We could even fill this out if we wanted already. Okay. Now you may be asking, oh, Cameron, what about A? Do we resume with A? Do we keep going? And the answer is no. You don't want to resume with A. Like I said here, we put it at the back of our queue, so we're going to move on to C and D. Okay? Now let's take a look at C. C is supposed to arrive at 5, and it starts at 3. So this is a very, very, very interesting situation here. C is supposed to arrive at 5. Are we at 5 yet? No. So we can't start C. So what's left? Well, we actually now have an exception. We can resume A. We are allowed to resume A. Okay. So let's go ahead and we're going to resume A. We're going to take this out of our queue. We're going to go 1 and 2. Okay. Now A, we've already used A 1, 2, 3 times, and it still demands 4. So now we're at a crossroads here because this is supposed to arrive with 5. C is supposed to arrive at 5, right? So what's going to happen? Well, A has 1 left. C has 3 left. Okay. So the shortest remaining time, whatever has the smallest remaining time. A has the smallest remaining time, so we're just go ahead and finish A. Because A only has 1 left. This still has 3 to go, so A will get priority here. And we will finish off A. Okay. So now all that's left in our queue is C and D. So let's go ahead and look at C. So C is scheduled to start at 5. Of course it didn't, but that's okay. So now we're going to go to 3, but wait a minute. D is supposed to start here at 6. So what's going to happen? Well, when we're at this crossroads here, we take whoever has the shortest remaining time left. We haven't even started C, so it's 3 against 1. What has the shortest one? It's going to be D. D has the shortest one. So we're going to go ahead and do D. And we can move, technically in our queue-wise, this is what it looked like before. And now because we were at our crossroads, we're going to move C down our queue with 3 left. So now C is going to become moved down here because of these crossroads that they're at. And we're going to prioritize D. Okay, so we're going to do D, and D is only going to have to do it once. Perfect. And now, once D is complete, we can now finish C finally, or I guess start C. for what the heck? That's kind of cool. 1, 2, 3. Okay. Okay. Any questions? I know this is this is the hardest one of the hardest ones. I'm sorry. What? Okay. So if C's arrival time was less, we'd do C first, right? Yeah. Yeah, that's exactly right. That's exactly right. We would do C first if well, wait, no, not the arrival time. Uh, if the arrival time was less, so that's why we did C, but it was supposed to arrive like we've already passed the window for C, and now we're at where D is supposed to start, and D it was supposed to um, start at 6. So when we begin doing C, we have to compare uh, who has the shortest remaining time. Yeah, yeah. So if the processing time was 1, then yes, we would prioritize the shortest remaining time. The remaining time of this would be 1. Now, if they were the same, if this was 1, 1 is not less than 1, but you go in lexicographical order. That's always your default. So then we would do C and then go to D. Yeah, no, clock policy won't be on the extra credit. For this, do we also continue the current process if they are the same time? What do you mean by same time? Like if they had the same service time? If they have the same service time, yes, you would continue C. Mm-hmm. Yeah. Okay. Does this make sense, everyone? Is everyone cool with this? I know you're definitely gonna have to rewatch this a few times, but that's fine. But that is SRT. Okay. If we had 2 processes in the back of the queue, say C, D, A, and B, and there's a similar gap where the next process doesn't start, do we compare A and B and continue as A as it's with the queue? Okay, that's a good question. So I think I see what you're saying. So if we have C, D, A, and B, where these have some remainders, we'll just say N, right? And then let's say that C and D haven't arrived, I think is what you're trying to say. Like let's say we're here, C and D aren't ready. Well, you just follow your queue, right? Technically, you don't have to worry about like you do A until you reach the crossroad where C is supposed to arrive. Okay. And if you still have A left over and it's still less, then you'll move it. But he's not going to give you something that complicated. But yes, technically you would have to compare A and C if while you were doing A, it reached the place where C is at, or C is expected to arrive. Can we revisit SPN? I think it's supposed to be non-preemptive. Yeah, what do you mean by non-preemptive? Can you short how these algorithms are different? Okay, yeah, let me go over all of them real quick. Just a quick little summary, okay? First come, first serve. Very simple. You do A, then you do B, then you do C, and then you do D.
I think I should kind of screw up on the shortest process next. The process is supposed to finish like throughout the entirety because it's non-preemptive. So what that means is like the process service time needs to complete before it moves on to another process.
Or
like
SPN?
That means like yeah, for SPN, like you can't cut it off because shortest remaining.
Oh, that's right. You can't. Yeah, you can't. Okay.
Yeah.
Okay. Yeah. So shortest processing next. So yeah, you wouldn't cut it off. SRT is the only one where you cut off.
Yeah.
Okay. Yeah, you're right. Because this is pretty much the same thing. I'm sorry. No, you're right. It would be non-preemptive. So then technically, let's say you were to get, it's actually exactly the same thing as first come, first serve, except what you're doing is you are going to essentially do the, you're going to put in the order of, again, A, B, C, and D. So we do A, right? And then, yeah, so then let's see here. You would do technically, wouldn't you, Jason, wouldn't you do C, right? If this was supposed to be, let's see, 3. No, you would do B. It's a pretty bad example, actually. Because then technically you would just be doing B here for the whole time. For 5 times. And then, okay, I see the overlapping. And then I'm pretty sure you would do D because this has the shortest processing time. Right? Jason, do you remember?
Yeah, you have to do D next.
Yeah, then you would do
because
D
it
next. So,
has-
okay, I'm sorry, guys. So let me re-explain this real quick. Yeah, I'm so sorry. Okay, so basically all this is, right, for shortest processing time is next. You, like someone said, it's not preemptive. So you would do what you need to do, right? So we start with 0 and then we go to 3. Now, even though B is supposed to be arriving at 2, you keep A going. You would just keep A going because its processing time is shorter than B, right? And now if you look here, we have 3, right? We aren't at 4 yet, and 4 is supposed to be where C arrives. So we can start with B. So we can start with B here. So B, we'll go ahead and do 1, 2, 3, 4, 5. Okay, so just go ahead and just fill it all in. Now you may be asking, oh, but why didn't we stop like I did in the other example? Well, because technically we can do B because C hasn't arrived yet. And in SPN, you have to let it fully go out. Okay, like you have to, once you start it, you can't stop it. Okay, so look at it like that. Once you start it, you can't stop it. Okay, so we have to let B go all the way to 8. And now we see, well, C was supposed to arrive at 4 and D was supposed to arrive at 6, right? But when it comes to a crossroad like that, right, if we look at our queue, we finish A, we finish B. Now we're supposed to start C, but C is overlapping with 4 to 4, and then it's 6. So C is we've already way past C and D. So what you prioritize is you prioritize the shortest processing time. So in this case, 1 is smaller than 4, so you would prioritize D in this case. Okay, so sorry I confused y'all, but you would prioritize D in this case because D has the shorter processing time, and we're at 8, which means we're well past the arrival time of 6 and 4. Okay, and now we just do D, and then after that we just finish with C. Okay, I think for my example here I was looking at the wrong one. Sorry about that. Okay, so I know I just did a 180 on y'all, but so yeah, that basically. Look at SPN as no matter what, like if it's allowed to go, it's gonna finish no matter what. You don't have to worry about all the cutting up like this one, but for here, or yeah, for SR, excuse me, for SRT, all the cutting up, you don't have to worry about the cutting up. For SPN, you just have to once it's good to go, it's good to go. Okay, so I want to make that nicer, but it's fine. Okay, so does that make sense? So we start with A. A goes to 1 to 3. B is supposed to arrive, and A didn't overlap with anything else on than B, so we let B finish. B did overlap because we finished at A, so it overlaps with 4 and 6 with C and D. So now, okay, which one do we pick? Well, you got to pick the one with the shortest processing time. So D has the shorter processing time, so we go ahead and let D run, and then finally we let C run. So technically, you could say you move C to the bottom of the queue, but the queue isn't super important in this one, more the other ones. Okay. Yeah. Okay. Sorry about that. I apologize. So, all right, Jason, do you want to do HRRN?
Yeah, I'm alive. All right, let's do it. Okay, so let me go ahead and share my screen as well. Okay, my phone's gonna die pretty soon. Hang on. It's been a long day, man. Sorry. All right, so highest response ratio next. Okay. All right, so can everybody see my screen? Am I in the right chat? I should be. Okay, so why is this not refreshing? What is going on? Sorry, give me like 1 second. All right, so highest response ratio next. Okay, so I went ahead and just stole Cameron's numbers. So same thing here. You'll have the arrival time 0246 and the service times 3541. Okay, now this one is literally just like a purely mathematical one. You just plug numbers in and you calculate for whichever ratio is the highest, and that will determine who goes next. So same thing here. I'm gonna go in and just draw the graph since we like our good old graphs right here. So A, B, C, and D. And this is a non-preemptive algorithm, meaning you will just run the entire service time all the way through, regardless. Okay. So at time 0, A arrives, and that's the only guy that arrives in the queue. So we're just going to run the entirety of it. So, okay, hang on. Let me write this a little bit better. So A here. So 1, 2, 3, 4, 5, 6, 7. No, I'm not going to say it. 8, 9, 10, 11, 12, and then 13, right? Okay, so A is going to run 3 times. So it's going to run 1, 2. And at time 2, what happens? Well, B is going to be in the queue. Okay, and because this is non-preemptive, A runs throughout the whole thing. So A runs through, and we finish A off. So A is going to get finished off. Okay, now B is in the queue now. So we need to run B next. So B gets ran 5 times, and because it's the only thing in the queue, you don't need to calculate anything if it's the only thing in the queue, right? So B is going to run 5 times, so all the way across, and it's going to go all the way to 8. Beautiful drawing, I know. Now, at time 4, C goes in, and at time 6, D goes in. So both C and D are going to enter the queue by the time that B finishes. I kind of went that super quick, but so again, like at time 4, C goes in, time 6, D goes in. And because this is non-preemptive, non-preempt, okay? So the process gets to run the entire way through before somebody else can pick up, okay? So now at time 8, all right, we need to calculate the ratio for C and D, okay? And whichever has the higher ratio, hence the name highest response ratio next, okay? It gets to run next. So how do we calculate this? Now we need to get the wait time plus the service time divided by the service time. So how do you calculate the wait time? Well, what is the arrival time of C? Well, the arrival time is 4. And how long has it been waiting? Well, so C is supposed to arrive right here and D is supposed to arrive right there, right? So if C arrives right here and we're at this time right now. So what would the wait time be? Well, it's going to be 8 minus the arrival time, right? Because that's how long it has been waiting for. So 8 minus 4. So this would be the C's ratio. So this would be the wait time plus service time. Just follow the formula right here, right? So what's the service time? Which is 4. It's right here, right? Plus 4 divided by 4, which is the service time. Just look at this formula right here. Okay, so what would this number be? It's going to be 2. D, we just do the same thing. So at D, what is the wait time? Well, right now the time is 8, and D has been waiting since 6. So 8 minus 6, that's the wait time, plus what's the service time? Well, it's just 1 right here, right? So plus 1 divided by 1, which is equal to 2 plus 1 divided by 1, which this should be 3. So between C and D, which ratio is higher? Which one is higher, guys? D, perfect. Yes. F, yeah, that's probably going to be your grade. I'm just kidding. So 3 is greater than 2, right? So D gets to run next, right? So we're going to start at D, and it's going to go to 11. So 3 times. And then D. I can't do this, man. Dude, I should have drank caffeine before this. Anyway, so now because C is the last one in the queue, C gets to run the remaining, which has 2 left. To scratch things off, what are the final times? So A gets to finish at 3. Where does B finish? B finishes at 8. C finishes at the very last time, which is 13, and D finishes at 11. The service time for D is. Did I screw up? My gosh, I'm sorry. Yeah, you're right. I'm sorry. Okay, so let me draw this box a little better. So this goes all the way to 12, actually. I'm so sorry. And then 12 to 13, that's, oops, so just 1. Right, because this has 4 and this is 1. So this will be, so the first finish time for A will be 3, B will be 8, C will be 12, or excuse me, 13, sorry, and then D will be 12. Turnaround time, you really don't actually need this for the exam, but just going to calculate it for fun. So 3 minus 0, so this would be 3. 8 minus 2, which is 6, and 13 minus 4 is 9. I know the numbers are all over the place. I'm sorry, but 12 minus 6 is 6. And that's it. Worst TA's NA. Okay, buddy. All right. Wouldn't D end at 9? No, D ends at 12. D ends at 12. This is just saying like where C and D enters. Like ignore this. And C is 4 service time. Yes, that's right. Yes. Yeah. Here, let me put this a little bit better. And again, like, I'm sorry that we're so tired, but go ahead and like watch the old videos with the Excel sheets. Like they're perfect, clear, and they explain everything as well. And it has a different example too, so you can practice more as well.
I thought it was higher ratio next.
Exactly.
So
Yeah.
wouldn't D go before C, which is why people are saying it ends at 9?
I mean, yeah, 3 is above 2, right?
I think you have their service times mixed up
Wait. Okay.
on
No,
the
no,
graph.
'cause- so D has the ratio of 3 and C has the ratio of 2, right? So D goes first. So it goes from 8 to 12, right? That's where D goes, 8 to 12. And then C goes from 12 to 13.
But D has the service time of 1.
Yeah. D has. Oh my gosh. Thanks.
Yeah,
Okay.
I think what
Okay.
I see it too. Yeah.
Dude, this is actually the worst like TAs in NA, bro.
Yeah, I mean, I think
Um,
look, at the end of the day, all you have to understand is just that ratio, right? It's the
Yeah,
same process that I
just,
taught.
yeah.
Just when you come at a crossroads of what's next, you just do the ratio formula and you pick whatever is
Yeah.
the highest.
Sorry about that. So yeah, exactly. So the finish time, just to mark things off real quick. So A finishes at 3, B finishes at 8, C finishes at 9, and then or excuse me, sorry, C finishes at 13. I'm sorry, and then D finishes at 9. So you guys are right. Yes. So again, like I'm not gonna lie, we're probably just gonna scratch the recording. Like just watch the old videos. They're like much better. But that is highest response ratio next. So again, just use the formula and whichever has the higher one, run it and you win. Cool. Okay. Any questions on this before I move on to file system?
Yeah. The only time you interrupt is the is the shortest. Is the sorry, hold on. SRT. It's the only time you interrupt. Okay. And round robin. You do interrupt in round robin.
Okay.
Okay.
File system. I'm just because we're running.
Yeah,
like,
last
we're-
one.
Yeah.
Also,
and
real
we'll-
quick, for those of you listening,
Mhm.
your extra credit tomorrow will most likely, not confirming, but if I were to guess, would probably be FIFO. Okay. That's what I would assume. It's not guaranteed, but I would really study FIFO for tomorrow. Okay. That's it. That's all I'm going to say.
6. All right. Okay. So consider okay. So we're just gonna go over file system real quick. This one is pretty simple. You basically have to plug in some formulas and you win. Okay. So consider a 32-bit file system and 4K byte block size with, who cares what this word means, format that has 12 blocks for direct access, 1 block for single, and 1 block
Jason,
for
your
double.
stream is paused.
Is it paused? Great.
Mhm.
Perfect. Thank you so much. Thank you, Discord. I really appreciate that. Is Discord being nice to me now? Hopefully.
Yeah, you're good. You're good. We can see.
Cool. Okay. So again, consider a 32-bit file system, 4K byte block size with format that has 12 blocks for direct access, 1 block for single indirect, and 1 block for double indirect. A lot of fancy words. Who cares? Just solve the question and then win. Okay. So direct level capacity in kbyte. So let me ask this question, right? If there is 1 block, or excuse me, if there's 12 blocks for direct access, okay, and each block is worth 4K bytes. So what is that in total? Again, if 12 blocks and each block is worth 4K, how many K is that? No, not quite. There's 12 blocks. Each block is worth 4K. There's 48K. Yeah, exactly. So it's just 12 times 4. That's it. 48. Right? Now, if this were to ask you, let me ask a question real quick. If this were to ask you to count this not in K, like this case says, you cannot simplify your answer by using the information units. And you actually have to punch out how many bytes there are. Then you have to do 12 times 4096. Okay? Because 4K bytes is 4096 bytes. Okay? We're in CS. We're not in business. So it's bytes stuff. And then you will calculate that. But in this case, it will just be 12 times 4 because we're just asked to do K bytes. So this is 48. Okay, moving on. So number of blocks available for the first level of indirection. Now, if we're in a 32-bit file system, okay, or let me ask this first, right? We have 1 block right now, and there is 4K bytes. Okay. How many bytes is that? First of all, that is 4096 bytes, and I just mentioned that before. Okay, and there's 1 block, so this is just times 1, right? And if we're in a 32-bit file system, how many bytes are in 32 bits? Does anyone know that? So let me repeat the question. If there's 32 bytes, or sorry, 32 bits, how many bytes is that? 4, right? Why is it 4? Exactly. Okay, so there, in 1 byte, okay, how, Jesus Christ, what just happened? Okay, how many bits are in 1 byte? 8. Okay, so there is 4 bytes and 32 bits, meaning, where was I doing again? So times 1 block divided by 4 bytes. So divided by 32 divided by 8, right? Because that's how many we can have blocks available for that level. So in other words, we divide 4096 bytes by 4 bytes per block. Meaning this will get us 1024. And honestly, for simplicity, you can honestly safely assume that this is always going to be 1 block for single and 1 block for double. Like, I don't think I've ever seen an exam so far that this number is not 1. So you can just like if this is easier for you, you don't have to even like multiply anything. This is kind of the formula to solve it. If Rincon puts this,
still
like
still tell him just in case.
yeah, just in case, like if this is another number, then like multiply by another number, like 2, for instance, if it's 2, right? It's just I highly doubt it. Okay, but yeah, 1024. That is the number of blocks available. Now the very last one, this is the easiest one, super fun. Okay, square it, you win. What is a square? Now, why is this squared? Actually, let me explain this real quick. Now this says 1 block, so it's just 1024 times 1 block, because that's how many blocks is required for the second level or indirection, and then you just square it, just because that's what the formula says. So don't ask me why, honestly. 1024 squared, it's a big number. I look it up. No. This, there you go, and then you win. Any questions on this? Now, if you do want to see like the formulas, I can't find it on my work laptop anymore, but there was one in this exam review before. It's like towards the very end. So if you want to like look at the specific formulas, you can go ahead. I'll send in the resources right now. But honestly, with these 4 videos, you should get like 167 on your exam. So you should be good to go. Okay, cool. All right, awesome. Now, one last one, the fair share scheduling algorithm, and then we can let you go. I was trying to like, oh my God, I was in the middle of designing this. It really doesn't matter here. So this is CPU count, and then this is group CPU. Okay, this one is actually kind of confusing, but I would highly recommend just watching the video in the exam review if you want to understand it a little bit better. But this is going to be like this simplicity is what you would expect on your exam. Now, don't take my word for it. I don't know where Rincon's going to do these numbers, but you should only have 2 like processes going for this one. Typically, most likely. Again, don't take my word for it. It could be more. It could be more than 2. So definitely do read over the slides and then do watch the old video for the exam review 3 if you want to gain a better understanding of this. Now, so for this question, the idea of, I don't know why I drew that line. The idea of fair share scheduling is that you're running these CPU counts as you're going through, and you're going to divide them fairly depending on the priority of each processes. So let me rephrase this a little bit better. Whenever we have the process with priority, whichever one has the higher priority is going to run its counts, and then we just basically check the entire processes, and we notice whichever one has the higher priority gets to run next, and we fair share as we go through it. Okay, so now in this example, we're going to just do interrupts, which are, you can safely assume it's going to be 60. It's always going to be 60 just because there's 60 seconds in a time. Okay. And again, this will be in the exam review 3 as well that I posted in the resources if you want to go through it. And I also explained this like thoroughly as well in that part. So if you want to like read that resources in the channel, feel free to do so as well. So we're just going to quickly go over this. So